This is Unit 4, Video 8. In this video, we'll talk about how to write net ionic equations for neutralization reactions. In the previous video, we talked about how to write these for precipitation reactions, and they work the same way for neutralization reactions, and as you'll see, many more reactions. So, a neutralization reaction, remember, is when an acid and a base react. An acid begins with an H, a base ends with an OH, and the cation from the base and the anion from the acid will form a salt. What this means is that the cation from the base would be like sodium. Here's the cation from the base. The anion from the acid would be like chlorine. And these two form a salt, which is sodium chloride. And that's the idea. And then the second compound that's formed is water. And that's from the reaction of the active part of an acid and an active part of a base, HOH. So the molecular equation will actually look like this. HCl plus NaOH, giving you sodium chloride and water, a simple double replacement reaction as we've seen before. The net ionic equation will have H plus with OH minus to give you H2O. So really the heart of this reaction, the sodium and the chlorine really have nothing to do with it. They are the spectator ions. The heart of it is the hydrogen ion, the hydroxide ion reacting together to form water. That's really the essence of an acid-base reaction. At least a simple type of acid-base reaction. We'll show you a more complex one that is a little more in-depth. Alright, so we're going to actually try to write one using the same idea we've done, beginning with the full, complete equation and then breaking it down to the net ionic. So the first thing we'll do is write the equation as we've always done it, simply HBr plus KOH. So here we have HBr, hydrobromic acid, with potassium hydroxide, our base. And it's a double replacement reaction, so potassium replaces the hydrogen, you get potassium bromide, and you get yourself HOH, which is H2O. So really go ahead and write HOH as H2O. Now, if we put state symbols on these, the first two are aqueous. Now, we know this, all acids will be aqueous, and bases will also be aqueous unless otherwise told. So we'll assume these are aqueous. Now, when we get KBr, KBr is also aqueous because all potassium, all group 1 metal ions are soluble, and water is a liquid. So this is very similar to the precipitation reaction where we had 3 aqueous and a solid. Here we have 3 aqueous and a liquid. So this will follow the same pattern. What we'll do is we'll break apart, for the full or complete ionic equation, we'll break apart anything aqueous into its ions. In this case, hydrogen ion and bromide ion, like so. We'll do the same thing with potassium hydroxide, potassium ion and hydroxide ion. We'll do the same thing with potassium bromide since it's also soluble. Remember, anything soluble gets broken up like this. And bromide ion. Water does not get broken up because it is not aqueous. It is a liquid, kind of like the solid that didn't get broken up with precipitation reactions. So this is your complete ionic equation. And then if we recall, what we did is anything that appeared the same on both sides, we canceled out. In this case, bromide ion, notice, appears the same on both sides, so we'll cross those out. Potassium ion appears the same on both sides, so we'll cross those out. What you're left with is hydrogen ion plus hydroxide ion to give you water. And this is, again, the essence of an acid-base reaction. We bring that down, H plus OH minus, to give you H2O. And then we can go ahead and put state symbols on these. We can put aqueous, and then liquid. And this is your net ionic equation, what we want to get to. Net ionic equation. That's what the question asked for. So you just saw this in the previous slide, but here we kind of worked it out for you. And this will be the case with 2 acids which are soluble. An acid and a base which are soluble. Now we knew that this was aqueous because potassium is always soluble. We knew that this was aqueous because acids are aqueous, or you can also think that bromides are always soluble unless you're with one of the 3 robbers. Remember, silver, lead, or mercury. In this case, it's aqueous. So based on solubility rules, the first 2 reactants were soluble, and that's what made this net ionic equation nice and simple. Now, if one of these is not soluble, say if this was a solid, then net ionic equation will be a little different, and we're going to do that example. So here we want to write the net ionic equation between iron hydroxide and nitric acid. Now iron hydroxide, this is the difference here. This is still the base. This is our base, because all hydroxides are bases. This is our acid, obviously. But this base here is insoluble, because hydroxides are usually not soluble, unless with a group 1 ion or an ammonium, but iron is not one of those. So this actually is a solid, which will make this a little bit of a different net ionic equation. We're still going for the net ionic equation. We'll just get there a little different. Or we'll use the same method. You'll see it's not simply H plus OH to give you water. Alright, so iron hydroxide, let's go ahead and write that out. By the way, this is iron 3 hydroxide. There are two types of irons, possible iron 2 or iron 3. This is the 3 variety. So we have this with nitric acid. And we're simply going to do a double replacement reaction as we've done before. So in this case, as before, H replaces the iron, you get HOH. Now you say, well, we have 3 OHs. That's right, there'll be actually 3 H's in the end. So you'll still get HOH. In other words, you still get H2O for your product. It's the same idea as before. And then you get iron 3 nitrate. Now because it's iron 3 nitrate, make sure you put 3 nitrates with every iron. This, remember, is because iron has a +3 charge, nitrate has a -1 charge. You need 3 nitrates for every iron. Okay, in this case, let's go ahead and put the state symbols. This is going to be a difference. So here, our nitrates are always soluble, so we'll put aqueous for the nitrate. And we said this one was a solid, because hydroxides are usually not soluble, and it's not with an iron. Water is a liquid, and then iron nitrate is actually aqueous. This one is soluble, since all nitrates are soluble, so iron nitrate will remain soluble. Alright, so the rule was this: anything that's aqueous, we split up. If it's not aqueous, we keep it together. So iron hydroxide here will be kept together. So we'll actually put FeOH3, keep that as it is. Nitric acid does get split up because it's aqueous. And we get H plus and NO3 minus. I should say this: if the nitric acid was a weak acid, we actually would not split it up. So not only is it aqueous, it is also a strong acid. Strong acids, remember, by definition, completely break apart. We'll show you an example where if you have a weak acid, then most of the ions exist put together. So most of the acid as a weak acid exists not as ions, but as a compound. So you'll have to watch for that. Don't mean to confuse you at this point, but just a little note for the future. Water does not get split up, since it is not aqueous. And then iron nitrate does get split up, so you'll see the +3 and the nitrate with the -1 here. Okay, so the last step, remember, is anything that looks the same on both sides gets canceled out. In this case, that is just the nitrate. Only the nitrate is the spectator ion. So notice everything else looks different. When I say looks different, the hydrogen was by itself on the left as an ion. On the right side, it's teamed up with water. So it actually underwent some sort of reaction. Nitrate is the only one that didn't really undergo a reaction. It stayed the same, so we cross it out. Nitrate is then the spectator ion. So in this case, what we could do is simply bring the rest of it down. Let's go and bring down iron 3 hydroxide with H plus. And then you get an arrow, you get water, and iron 3. Let's go ahead and use state symbols for these. So you essentially just carry over the state symbols that were originally there. So if you have a solid, originally this is still a solid, the H plus came from an aqueous, so we put aqueous behind the H plus. Water is obviously a liquid, and this here, iron, came from an aqueous, so we'll put aqueous here. Now we do have to make sure we balance the equation. So to balance the equation, it looks like we have 3 oxygens on the left, so we have to have 3 oxygens on the right. That gives us 6 hydrogens. That's 3 there, and I'm going to put 3 more there. So make sure you balance the equation as well. And this is our net ionic equation. Notice it's not simply, this is net ionic equation. It's it's not simply hydrogen plus hydroxide to give you water. We retain some other compounds. So in reality, if you were to see this reaction in a beaker, the whole point of a net ionic equation is you're representing what truly happens in the beaker. What you would see is you would see iron 3 plus ions swimming around afterwards. So before the reaction, you would not see iron 3, you'd see iron 3 as a solid. You'd see it down here, iron 3, hydroxide. But after the reaction, you'll actually see Fe plus 3 swimming around. And that's the whole point of showing this, is we're showing what really happened inside the beaker with a net ionic equation. The complete, or the molecular equation is really not what's happening in the beaker. So it's all right to begin with the molecular equation, but really these compounds are not double replacing. Really what's happening is the hydrogen comes in and reacts with the hydroxide to form the water, and then the iron is liberated. The iron that was a precipitate, that was a solid to begin with, is then liberated to swim around in the solution. And that's the whole point. Hopefully this makes sense. Go ahead and try a few on your own. There should be, oh, there we are. Yeah, go ahead and try this one on your own. Same thing, calcium hydroxide here then would be the solid. So do the same thing, practice this one, and then we'll give you some more practice in class. This concludes video 8.